I just getting ready to start. But thank you for asking. Yeah, so welcome everybody. Good afternoon. Welcome to week 2, CSE215. So, how's everybody doing today? Good, good. Slightly more awake than this morning. Yeah, that works for me too. All right. Hopefully everybody turned in their homework. Any questions on either the homework you just turned in or anything we did last week, or anything else for that matter? Someone just ordered a burrito. That sounds good. All right, well, let's start off by taking a quick look at homework 2, which I just posted this morning. So let me bring up Canvas. And we haven't gone through everything that we need to for you to be able to do all of homework 2. We'll get through some of it today, some of it we won't get through until Wednesday. But I want to just kind of talk through a few of the logistics on this assignment, just in case there's some confusion. So homework 2, again, it comes from the text. So I want you to do the following problems. Section 1.5, do questions 2, 4, and 10. And then chapter 3, sections 3.1, 3.2, 3.3, do these questions. Chapter 3 is a section on logic. We're going to start that probably later on today, and we'll be pretty deep into it by Wednesday. But section 1.5, I want to talk a little bit about what that homework looks like. So we're going to talk about summations and sequences today also. So question 2, there's 4 parts to it, and for each of these parts, A, C, and D, you're going to do 4 separate questions, okay? And there's also a typo here. This should be the sum for I equals 1 to 3 of I to the n. So figure out what this sum is equal to for n equals 1, and write that answer down. And then figure out what this sum is equal to for n equals 2, and then for n equals 3, and then for n equals 4. And then figure out what this sum is, and write that down for part B. And then for part C, 4 answers. N equals 1, write down this sum, n equals 2, and so on and so forth. Okay, so you have a total of 4, 5, 9, 13 answers for question 2. Okay, and make sure I know what your answers are corresponding to. So, you know, 2A, n equals 1, show me the answer, n equals 2, show me the answer, and so on. What was the specific typo? Oh, the specific typo is for 2A, it should be the sum for I equals 1 to 3. And it says the sum from K equals 1 to 3, and then there's no K appearing in here. And you can still do that, but it's confusing. So just make this a sum from I equals 1 to 3 of I to the n. All right. And question 4, verify the following properties for n equals 3. So we know that if we have a summation of, you know, an expression that's 2 things added together, we can split those sums up into 2 separate summations and then add the results of those. But why can we do that, other than the fact that it looks reasonable? Why can we pull a constant out of a summation or put it inside each term? So I want you to think about these for just the case n equals 3. Write this out explicitly, write this out explicitly and convince me that those are the same things. Okay? This is something you do in calculus when you look at Riemann sums and you come up with the notion of integrals, right? We learn these rules that an integral of a sum is the sum of the integrals. The integral of a constant times a function is a constant times the integral of the function. Those come from these properties, right? So these are really powerful fundamental properties. So we're thinking about them in a very particular case, just where n equals 3. We'll talk in a few weeks about how to generalize these using something called mathematical induction. And then number 10, I just put a note that question A is pretty straightforward. You have to add 4 things, multiply 4 things. Question B, think about it before you try to actually multiply 100 things together. Try to find a easier way to do that other than just directly multiplying it. I am not muted as far as I know. And some people can hear me. So that's good. So this is a product symbol. It's like summation but product. We'll play with these in a few minutes. But this is just the product from k equals 0 to 3 of 2 to the k. So this is 2 to the 0 times 2 to the 1 times 2 squared times 2 cubed. And that's a symbol for an uppercase pi, just like sigma is a symbol for an uppercase S as in sigma sum. All right, so those are just details I wanted to mention on the next homework, which is due a week from today. A few people had some issues with trying to submit the homework as far as scanning it and stuff. My suggestion, right, spend some time experimenting, because you're going to have to do this, you know, throughout the Zoom days, and even without, you know, COVID. You always need to turn in scans of things for one reason or another. So spend some time really kind of digging into that. If you're using a camera phone, figure out, you know, how to set up light or a window or something so that you have, you know, a nice crisp image without a lot of shadows on it. Figure out how to set the focus on your camera, maybe how to set the resolution and so on and so forth. Get yourself some tools for adjusting resolution, doing color correction, inverting colors, whatever. Somebody suggests Adobe Scanner app. They say it's pretty good. If you have a scanner, right, there's lots of opportunities for lots of options for using that. If you're running Linux, Xsane has been around forever and is still a pretty good basic scanning tool. Seems to work with a lot of scanners now. But, you know, figure out some collection of tools that will let you, you know, scan things and crop them and rotate them and so on, and then get good at putting them into a Word document and exporting that as a PDF so that you can upload it. It's just one of those things. Yeah, MS Word works great. It's just one of those things to get good at, because it's a skill you'll have to come back to again and again. I use OpenOffice, LibreOffice, completely free software. Seems to work as well as anything else. So find a solution that works. All right, so let's talk about functions some more. So we started talking about functions last week, and we were describing functions as basically a map or a correspondence from elements of one set to elements of another set. And we typically have, you know, two sets like this. There's the domain, which might be X, and this was called the codomain, which was Y. And we said f is a function from X to Y. It means that points over here in X get mapped to points in Y. And there's not a whole lot else required for a function. The one thing that is required, and you learn this in calculus, is what we call the vertical line test. We cannot have one point in X mapping to two different points. We can't say f of X is both 5 and negative 17, because that's not what we call a well-defined function. What's f of X? Well, I don't know. It's either 5 or negative 17. That's not a function, okay, for us. But as long as each point in here goes to exactly one point in y, that's a perfectly fine function. And there's all kinds of sort of pathologies available. You could have two different points going to the same point over in y. That's perfectly fine. For example, f of x might be the function x squared. Well, f of 1 is equal to 1 and f of negative 1 is equal to 1. That's the kind of thing you're seeing in this picture here. Two different points, 1 and negative 1, both going to the same point 1. Still a function. Here's another kind of situation we can have. There might be some points over here that don't get mapped to from anything in x. Every point in x goes to exactly one point in y. And it may or may not be the case that different points always go to different points. But independent of those situations, we might have some points over here with no arrows pointing at them. Nothing maps over here. Again, if f of x equals x squared, there is no point over here, if we're talking about integers, that maps to the number negative 1. If we're talking about integers, there's no point over here that maps to the number positive 2. That's okay, it's still a function. Okay, but we're interested in these different characteristics of functions. So we have some terminology. So we can talk about an injective function. An injective function means this never happens. Okay, so let me give you a bit of a definition here. So a function f is injective. Let's say f goes from x to y. If f maps different x to different y's. That's a kind of loosey-goosey definition, but the spirit of it is, if I take two different points here, they're going to map to different points over here. So something like what we're seeing here. This is always the case with an injective function. Different x's go to different y's. If we have a case where even just two x's go to the same y, this is not injective.
Is this the same as like one-to-one functions?
It's exactly the same as one-to-one. All right. If we wanted to write this more formally, we could say f of x equals f of y only if x equals y. The only time two things map to the same value, let me not confuse this. Let's say f of x1 equals f of x2 only if x1 equals x2. So the only time two things over here map to the same value over here is if these two things are the same point. Right? Clearly, if x1 equals x2, f of x1 equals f of x2, because it's f of the same thing. But to be injective, we're saying the only time this happens is when you're mapping the same point. Okay, that's injective or one-to-one. The next kind of function we can talk about is surjective. So f is surjective if for every point y in the codomain y, there is some x in the set x such that f of x equals y. So f is surjective if every point over here has something mapping to it. If we have even just one point in y that's not mapped to by anything, then it's not surjective. If every point in y is mapped to from somewhere, then the function is surjective. We also call this onto. So these are just definitions to keep in mind, put on your note sheet. And then finally, a function can have both of these properties, in which case it's bijective. So f is bijective if f is injective and surjective. And this is sometimes called one-to-one onto. All right, so some examples. F of x equals x. So is this injective? Absolutely. It's injective because the only time that f of x equals f of y is if x equals y. So this is injective. It's surjective because any number x is mapped to by something, in particular x. And so it's also bijective. Now in general, we need to be careful about what the domain and codomain are. For pretty much any reasonable domain and codomain, this is always going to be true. But let's get specific. Let's suppose f goes from z to z. F of x equals x squared. Well, we already saw that's not injective because f of 1 and f of minus 1 are the same value. So 1 and minus 1 both map to the same value. It's not injective. It's not surjective because there's nothing that maps to 2. There's no integer whose square is 2. And so it's definitely not bijective. If we go from the positive numbers to the positive numbers, suddenly this is injective. The only time two positive numbers have the same square is if they're the same number. So if I tell you f of x is 4 and f of y is 4, x and y must both be positive too. So this is injective, but it's still not surjective because, nothing maps to 2. There's no integer whose square is 2, and so it's not bijective. If f goes from the integers to integers and f of x is the function x plus 1, that is also injective. The only time x1 plus 1 and x2 plus 1 are the same is if x1 and x2 are the same. Right? So just write down some points and start seeing where f takes those points. It takes different points to different values. So that's injective. And any number that we can think of in z is mapped to by this function. 17, well, that's going to be f of 16. Negative 5, that's going to be f of negative 6. So it's surjective and it's bijective. Now if f goes from positive integers to positive integers, it's still injective, but it's no longer surjective, because there's no positive integer which f will map to the number 1. Right? The only thing that you can add 1 to and get 1 is 0, and 0 is not in the domain. So this is not surjective, not bijective. So we can have lots of different combinations, and these properties are basically independent of each other. But it's basically a way to characterize these properties of certain functions. And it basically affects what this picture looks like. Surjective, every dot has an arrow going to it. Injective, no dot has 2 arrows going to it. Right? Every dot has, at most 1. And bijective, every dot has exactly 1 arrow going to it. Meaning it comes from somewhere in the domain, and different points in the domain go to different points. All right, questions on that?
If you have a number in the domain that doesn't go to any output, is the function still injective?
Then the function's not defined. The function has to have a value for everything in the domain. Or more likely, I would say that particular number is not part of the domain. But if it really is, then it's not a well-defined function. All right, and functions can be anything, right? I mean, I can make a function which takes an integer and returns an animal. And if the integer ends with a 6, it returns a cow, otherwise it returns a chicken. That's a perfectly fine function. It's a function from the set of integers to the set of animals. Right? I mean, it's a weird function, but it's a perfectly defined function, and we can talk about injectiveness and bijectiveness and so on and so forth. All right. So let's talk about summations. So this is probably more review for people. But let's make sure we're on common footing here. So, for example, sum from I equals 5 to 10 f of I. This is just a shorthand for f of 5 plus f of 6 plus all the way up to f of 10. So summation, some variable equals lower value, upper value, some function which presumably depends on this variable, is a shorthand way of writing add up all the values you get when you take f and you plug in 5 and then 6 and then 7, 8, 9, and 10. Put them all together. Okay, it's a good old for loop. It's a running sum. Set sum equal to 0 for I equals 5 to 10. Sum equals sum plus f of I. And one thing to note, just like in for loops, this variable, this summation symbol is kind of irrelevant, right? I could sum from high equals 5 to 10 f of high, right? Or more likely in a mathematical context, sum from j equals 5 to 10 f of j. That's exactly the same as a sum for x equals 5 to 10 of f of x. All right, so that's an interchangeable symbol. Okay, just like in a for loop, the variable we use is pretty much irrelevant as long as we use that same variable inside the loop. We could globally change it from I to j to k to haha, and we'll still get the same result. All right. Other things we can do with summations. Sum from I equals 5 to 10 f of I. Well, remember that's f of 5 plus f of 6. I'll write this out. Well, this is also the sum from I equals 0 to 5 f of I plus 5. Because this says set I equal to 0, well, f of 0 plus 5 is just f of 5. Set I equal to 1, f of I plus 5 is f of 6. And our last case, I equals 5, f of I plus 5 is f of 10. So we can have this change of index. And we haven't really changed the value of anything. We can also take this original sum and write it as, for example, the sum from I equals 5 to 7 plus the sum from I equals 8 to 10. Right, we can split it up into two or more sums. And that's not going to change the value. All right, and then we have properties like the one you're going to work on in your homework question. And so I'll just go the sum from I equals A to B, f of I plus g of I. And that's the same thing as splitting these sums up. And you can multiply by a constant and pull the constant out, just like in the homework question. And you can subtract, and so on and so forth. And again, this is why we get those nice rules for doing integrals. But they only get you so far. All right, we can also do infinite summations. And there's an assumed space we're working over. Everything we've been doing so far for summations, we're working over the integers, right? We're saying if we want to sum from 5 to 10, then we take on the values 5, 6, 7, 8, 9, 10. So it's a for loop where the unstated part is, I plus plus. We're going by integers. We could go over different things, right? But that gets into some very different mathematics. So we'll always assume we're summing over integers. But we could be summing over an infinite set of integers. So sum from I equals 0 to infinity, f of I is a shorthand for f of 0 plus f of 1 plus f of 2, and so on without end. And there's no point where we're going to say f of infinity. This infinity means keep doing this forever. And does such a sum make sense? Can we add up an infinite number of things and have it be meaningful? What do you think? Sometimes. All right, someone said the magic word. If the series converges. So we won't worry about telling when something converges in this class. But let me just give you an example. Right, sum of 1 over powers of 2, 2 to the I. So we're adding up reciprocals of powers of 2. Which is 1 plus a half plus a quarter plus an eighth and so on and so forth. And that actually does converge to just good old 2. So that infinite sum makes sense. whereas this sum does not. If you just add up reciprocals of consecutive integers, that blows up. It gets larger and larger and larger, so we would say this equals infinity, not because that's what your calculator will tell you, but because it gets larger than any integer we can think of. All right, another thing with summations is we can do double summations. So let's do the sum from I equals 1 to 5 of the sum from j equals 2 to 3 of 2 times I times j. And one way to think about this without panicking is just for a moment think of this part as something by itself. Right? Start from the inside and figure out what this is equal to, and once you know what that's equal to, replace this expression with that thing, and now just do the sum from I equals 1 to 5 of whatever you found this was equal to. And this is basically a nested loop. Yeah, you're right. This is for I equals 1 to 5, curly bracket for j equals 2 to 3, curly bracket, sum equals sum plus 2 times I times j, a couple of closed curly brackets. So let's just take this piece right here, and let's say the sum from j equals 2 to 3 of 2ij. Well, how do we do this? First we set j equal to 2, so it's 2I times 2. And then we set j equal to 3, so that's 2I times 3, and we add those together. So this is j equals 2. This is j equals 3. Well, this is 2I times 2. This is 4I. This is 2I times 3 is 6I. 4I plus 6I is 10I. So this expression right here is equal to 10I, which means we can take this whole thing and we can say this is the sum from I equals 1 to 5 of 10I, which is 10 times 1 plus 10 times 2 and so on, up to 10 times 5. And we can write those out. And that's just going to be 150. So if you see double or triple summations like this, break it down. Start from the inner piece, figure out what that is, replace this complex summation with that expression, and then do the sum of that expression. And if you had another sum out here, right, just work on that piece. Once you know what that's equal to, replace it with that expression, do the sum of that. And if we do real numbers, this is where we get double and triple integrals. So back to physics. This is how those are defined. Because integrals are nothing more than summations. They happen to be infinite summations of a particular type, but they're really just summations. That's why they're called Riemann sums. And so the more you know about doing summations, well, you basically know about doing integrals too. And if you want to do calculus in a computer program, all you got to do is know how to calculate a sum. Now, we can't write a computer program that sums from 1 to infinity, but, you know, we can go up to 100,000 maybe. 100,000 is almost infinity. And you do a pretty good job of calculating integrals of fairly complex expressions numerically by writing a program and just doing that Riemann sum as a big for loop. And this is how things that do numerical integration is basically what they're doing. All right, but we don't talk about real numbers in this class, so forget I talked about any of that. No, it's good stuff. All right, let's talk a little bit about sequences. So Let me give you some examples first. That's an example of a sequence. It's a sequence of 5 numbers. Here's an infinite sequence. 1, 2, 4, 8, 16. We can guess what the next numbers are, 32, 64, etc. That's an infinite sequence. Okay? Abstractly, we can just kind of think of a sequence as a collection, an ordered collection of things. Okay, a sequence of integers would just be a set of integers listed in a particular order, separated by commas. Could be a finite number of them, could be an infinite number of them. So here's another sequence. That's an infinite sequence. Some numbers occur more than once. The number 3 appears twice. It's still a sequence. And we can think of a sequence as a function. This is a function from a subset of Z to a set S. So for example, I might be thinking of a subset of Z consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And my function takes a 1 to a 1, 2 to a 2, 3 to a 1, 4 to a 3, 5 to a 2, 6 to 4, 7 to 3, and so on. And so if I want to know the nth term of my sequence, I just take this function and I say, what is f of n? And it'll be whatever the nth term of my sequence is. So again, functions encapsulate most things, functions and sets. Alright, so we might write a sub n, right? The nth term of the sequence is just f of n, where f is whatever function corresponds to this sequence. And sometimes we use the unfortunate notation like this. Okay, this is not a set. This is a sequence. Consisting of A1, A2, A3, and so on. So I'll mostly avoid that notation because it directly contradicts everything we've said about sets, and it's really not a set. But you'll see it sometimes in writing. All right, so why do we care about sequences? Well, there's a particular class of sequences called recurrence relations. So a recurrence relation for a sequence A1, A2, A3, dot, 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 is an expression for AI in terms of A1, A2 through AI minus 1. A recurrence relation is a way to express the nth term of a sequence by using the first n minus 1 terms of the sequence. for example, we might have a sequence where an is equal to 2 times an minus 1. And this is dynamite right here, by the way. We are talking about something that's going to like be the core of most of this course. Okay, we're going to come back to it a bunch of times in a lot of different forms. This is our first approach to it. We could define a sequence where the nth term of the sequence is twice the nth minus first term. And that almost tells us everything we need to know about the sequence. Except we don't know what the first term of the sequence is. If I try to find a1, assuming that's the first term, that would be 2 times a0. Well, if the first term of the sequence is a1, what does a0 even mean, right? So this is not always well defined, because in particular, if n is 1, this is meaningless, right, if I don't have an a0. So I need an initial condition where I'm going to say a1 is equal to, I don't know, let's just say a1 is equal to 1. Okay, these two things taken together tell me everything I need to know about the sequence. Because I know a1 is equal to 1, I know that a2 from this relationship is equal to 2 times a2 minus 1, which is 2 times a1, which is 2 times 1, which is 2. And now that I know a2, guess what? I can find a3. It's 2 times a3 minus 1, which is 2 times a2, which is, well, I already found out a2 was 2, so a3 is 2 times 2, which is 4. And I can bootstrap up my entire sequence from this relationship and this initial condition. This is recurrence. As in recurring frequently. So recurrence relation. All right, so this is an initial condition. And this is, in this case, the recurrence relationship. Recurrence relation. All right, here's a different example. Let's say an is equal to n plus an minus 1. And let's say a1 equals 1. All right, so a1 is equal to 1, because we know that from our initial condition. a2 should be equal to 2 plus a1, which is 3. a3 should be equal to 3 plus a2. 3 plus 3 is 6. a4 should be equal to 4 plus a3, which is 10, and so on. So this defines the sequence 1, 3, 6, 10, 15, 21, and so on. And these are called triangular numbers. Each of these numbers is the sum of consecutive integers from 1 up through n. So the fourth number is 1 plus 2 plus 3 plus 4. The sixth number is 1 plus 2 plus 3 plus 4 plus 5 plus 6. And this is a very succinct way to describe these numbers. An initial condition and a recurrence relation. Let me change this example slightly. an equals n times an minus 1, and a1 is equal to 1. So play around with that for a minute, write out some examples, and somebody tell me what this sequence corresponds to. All right, one person's only getting ones. An will be n times the previous term. So as n gets bigger, your an should probably get bigger too. All right, we got some answers coming in saying factorials, and that's exactly right. So a1 is equal to 1. If n is equal to 2, a2 would be 2 times a1. 2 times 1 is 2. a3 would be 3 times a2, which is 3 times a2 is equal to 2, which is 6. And a4 will be 24, and so on. So that's a way to define factorials. And this idea of an initial condition and then this recurrence relation, that's going to come up again and again. It's going to come up in our next unit when we talk about proofs and we move to mathematical induction. And these things pop up in real life in lots of different ways. So let's say you put money in the bank. So when I was a kid, you could get 8% interest on a savings account. You put $1 in, and a year later you would get back $1.08. Right? Interest is negative in some parts of the world now. It might go negative in the U.S. at some point. They've talked about it. But let's imagine, this happy world where you get 8% interest by putting money in the bank. Okay, so 8% annual. So put your $1 in the bank. A year later, you get back $1.08. All right, so let's suppose P sub I equals your amount of money, what we call the principal, amount of money at time I. And I'm going to start from time 0. That's when you deposit your money. Let's say P0 is $100 that you put into the bank. Well, the way you find your principal at time I, it's your principal at time I minus 1 plus 8% of the principal at time I minus 1. Right, so next year you take whatever balance you have now, you add 8% of it, that's what your balance is a year from now. So it's 1.08 times PI minus 1. So P1 is 1.08 times 100. P2 will be 1.08 times 1.08 times 100. P3 will be 1.08 times your principal at P2, which is 1.08 times 1.08 times 100. And we can generalize this and say your principal at time I will be 1.08 to the I times 100. or more generally, 1.08 to the I times your initial investment. Or for an annual interest rate of R, 1 plus R to the I times your initial investment. So these things pop up in all kinds of situations. Bacterial growth, population growth in general, and so on and so forth. All right, let me do one more sequence just because it's another topic that's going to come up a lot in this course. Let me give you two initial conditions. A1 is equal to 1, A2 is equal to 1, AI is equal to AI minus 1 plus AI minus 2, and that's for I bigger than or equal to 3. So if we write this out, the first term of our sequence is 1, the second term is 1. The third term should be the sum of the second and first terms. 1 plus 1 is 2. The next term should be the sum of the two terms before it. 2 plus 1, this should be 3. The next term will be the sum of the two terms before it. 3 plus 2 is 5. The next term will be 5 plus 3 is 8. The next term will be 8 plus 5 is 13, and so on. So yeah, this is the Fibonacci sequence. And Fibonacci sequence is famous. It pops up all over nature. It pops up in art. It pops up in music. It pops up in population growth. It pops up if you look at the petals on a sunflower. It's one of these things that, you know, is fairly abstract mathematically, and it turns out to be seemingly fundamental to a lot of things in our real world. And so we'll explore this from time to time throughout the course. All right, so that's some things about sequences. Let me talk really briefly about matrices. We don't do a lot with matrices directly in here. We touch on matrices in ECS120 for solving equations, and when you do linear algebra, that's all you're doing is matrices. But let's do a quick rehash of matrices, just because it's kind of topical. So a matrix is a bunch of numbers written in a two-dimensional way, right? That's my approximate definition. So here's a matrix. It's a 2 by 2 matrix. Here's another matrix. It's also a 2 by 2 matrix. And we can do things with matrices just like we do with numbers. We can add matrices. So to add matrices together, we just add each element. So A plus B would be, well, 1 and negative 1 is 0, 2 and 0 is 2, 4 and 1 is 5, 7 and 16 is 23. We can subtract in the same way. We can multiply matrices by constants by just multiplying each element of the matrix. So I could say 5A, and that's really just A plus A plus A plus A plus A, and if you work that out, that's going to turn out to be 5, 10, 20, and 35. And we can multiply matrices. And so multiplying matrices is a little bit of work. So this upper left entry we get by taking the first row and the second column. right? First row of the first matrix, first column of the second matrix, and doing what's called a dot product, which means multiply first element by first element, second by second, third by third, and take the summation. So this is 1 times negative 1 plus 2 times 1. First row, second column, this value right here will be first row here dotted with the second column here. So 1 times 0 plus 2 times 16. Second row, first column, we'll take the second row here and the first column and dot them. So 4 times negative 1 plus 7 times 1. And second row, second column, we'll take the second row here and the second column here and dot them. So this will be 4 times 0 plus 7 times 16. And you calculate those and you get another 2 by 2 matrix. Yeah, it's very much like foiling. Alright, so a couple of things to know about matrices. In general, A times B is not the same as B times A. It could be, but in general it's not. And in some cases this isn't even well defined because the dimensions of your matrices have to have certain relations to each other. So multiplication is not necessarily commutative. Second thing, there's always an identity matrix. For a 2 by 2 matrix, this is the identity. And it turns out if I take any matrix A and multiply by the identity, I get back A. And I can multiply on the left or the right. So there's a unit, right? There's something like a 1 that you multiply any matrix by and it doesn't change the matrix. There's a 0 matrix we can add things to, that's just this. And any matrix A plus this is just going to be A. Because addition is easy, just add each of these to the elements of A. It doesn't change the value. Alright, we can transpose a matrix. And transposing just means swap the rows and columns. So this first row becomes the first column, this second row becomes the second column. And that's a really inexpensive operation to do. And we say A is symmetric if it's equal to its transpose. Yeah, I can't draw a symmetric matrix off the top of my head. Well, the identity matrix, for example, is symmetric. Because if you swap the rows and columns, you get the same matrix back. Alright, the last thing to know about matrices is we cannot in general divide matrices. There's no well-defined meaning to A divided by B. But there's something almost as good. In some cases, we can define an inverse. So A inverse is a matrix such that if you multiply it by A, you get the identity. And inverses don't always exist. Not every matrix has an inverse. If it does, it's a matrix that when you multiply by the original, you end up with the identity. And a lot of modern life boils down to trying to calculate the inverse of a matrix. That's how finance is done, that's how statistics is done, that's how machine learning is done. A lot of the stuff we spend our lives doing these days really boils down to inverting matrices. And if you have a really efficient way to invert a matrix, you wield a lot of power. Right, and so this is a lot of linear algebra. Linear algebra is three things. And some courses only teach you one of these, some teach you two, some teach you E3, all three. Linear algebra is three things. One, it's the study of matrices, okay, like we're talking about here. Two, it's the study of simultaneous equations, which comes down to matrices. That's the link we learn in ECS120. Three, it's the study of geometric spaces and embedding spaces in other spaces, and looking at planes and hyperplanes and things like that. And it turns out all three of those things are exactly the same. Okay, if you understand one, you just have to switch the language from, say, matrices to simultaneous equations, and you understand the others. Okay, so if you haven't taken linear yet, look forward to it, because it's a beautiful subject. And it ties into everything that we do as computer scientists. And it's, you know, the underpinnings of modern machine learning and all kinds of stuff like that. But it can be tedious at times because, you know, you're doing stuff like this. All right. So that's a really, really fast review of matrices. Other than to say, oh, there's also something called a 0-1 matrix. We can have matrices where all the elements are, you know, binary quantities. And matrices don't always have to be n by n. They could be 2 by 3. They could be 1 by 10. But I'm mostly picking on n by n. And if we have these binary matrices, we can talk about doing Boolean operations on them, and just doing those element by element, and so on. Oh, someone changed the DPI on their mouse and it closed Zoom. Yeah, I've had almost the exact same thing happen. All right. Any questions, comments on that? Like I say, that's probably review for most people, and we don't go a whole lot deeper into it in this course, but we'll come back to some of these topics and tie them into other things throughout the next 10 weeks. All right, let me talk about two fun things. First, let me talk about Russell's paradox. So this is a century plus old thought exercise that kind of ruined some people's days. When we first started talking about sets, we said a set is a collection of things. And that works for most of what we're doing with sets, right? So it could be pens or you know, types of salad dressing or whatever. We don't really put a whole lot of constraints on what can be in a set. But it turns out we really need to, because we can get into bad situations by letting sets just be collections of whatever we care to put in a set. So let's look at Russell's paradox. Russell's paradox is one of these examples of what so-called naive set theory can lead to, and it led to the development of very rigorous axiomatic set theory, something called ZF or ZFC set theory. So here's where Russell's paradox comes from, and yeah, there's already some stuff in chat talking about this. So let's have a definition. So we know about subsets, right? The set of positive integers is a subset of the set of all integers. And in fact, the set of integers is a subset of itself, and the empty set is a subset of everything. All right? So I'm going to make a definition that involves subsets. So a set S is called self-consuming if S is not a subset of itself, but if S is an element of itself. So a set is called self-consuming if it contains itself. And that's a really weird thing to expect a set to do, to contain itself. That doesn't even make sense, right? How can a set contain itself? Well, I don't know. It probably can't. But we can define this term self-consuming anyway. And we can say, if this set contains itself, then it's self-consuming. All right, so the set of integers, for example, is not self-consuming. The set of integers z contains 1, contains -5, does not contain z. So that's not self-consuming. The set a, b, c is also not self-consuming, because it only contains 3 things, a, b, and c. It does not also contain this set. Okay? And it's very hard to imagine a self-consuming set. But nonetheless, I've defined it, right? And, you know, if no sets are self-consuming, well, this is still a perfectly valid definition, right? Just like I can define, you know, a flying cow as a cow that has wings and can fly. Well, there may not be such a thing, but my definition still stands, right? All right, so here's what we're going to do. Let B equal the collection of all sets that are not self-consuming. So I'll write SC for self-consuming. So let B be the collection of all sets that are not self-consuming. So what are the things in this set B? Well, it certainly includes the set of integers. It includes the set A, B, C. It probably includes the set of reals. And, you know, most any set that you can think of is probably in this set B. Okay, it's any set that's not self-consuming. So we've got a definition of self-consuming. We've got a set B. So here's our question. Is set B self-consuming? And so think about that for a minute. It'll take about 60 seconds and kick that around and think about, is B self-consuming or not? And imagine being like, you know, in the early 1900s and playing with set theory and stumbling across this for the first time. And then trying to explain to your colleagues. Right? So yeah, this is a paradox, right? Because we suppose the answer is either, you know, yes or no. Well, let's explore both of those answers. So if yes, if B is self-consuming, then B is contained in B, because that's what it means to be self-consuming. But the way we constructed B was all the sets that are not self-consuming. And so if B is in this set, B must not be self-consuming, which contradicts our assumption that it was. So that leads to a contradiction. Since B cannot be self-consuming, we must assume, therefore, it's not self-consuming. Well, if it's not self-consuming, then it should be in this set B, because B contains all the sets that are not self-consuming. So therefore, B is contained in the set B, and therefore B is self-consuming, because that's what it means to be self-consuming. And so if it is self-consuming, then it's not. And if it's not self-consuming, then it is. And so that's a paradox. So these things pop up, okay, in different situations. So there's the I am lying paradox where Kirk's trying to overwhelm Harvey Mudd's androids, um, or Harry Mudd, and he tells the android everything I tell you is a lie, and then he says I am lying, right? And it's a paradox because if you say you're lying but everything you say is a lie, then you must be telling the truth, but you can't be telling the truth because you said everything you said is a lie, so you must be lying, and it goes back and forth. It's exactly the same thing. Yeah, it's a classic episode. All right. This is the same way that you prove that there's more real numbers than there are integers. Okay, it's another form of what we can call a diagonalization argument. It's a really powerful technique. And you basically set things up in a very methodical, deliberate way so that you do one more step and suddenly everything sort of turns on itself and introduces this contradiction. And so we have 5 minutes left. Let me see if we can prove that there's more real numbers than there are integers. So let's prove the cardinality of R is strictly bigger than the cardinality of Z. And let's do this by another contradictory proof. So suppose that the real numbers have the same cardinality as the integers. Okay? If that is true, then there is a function f from the real numbers to the integers, which is 1 to 1. Let's just say is bijective. In other words, there's a 1-to-1 correspondence between integers and real numbers. That's what it means to say two things have the same cardinality. It means we can come up with an association where every real number corresponds to an integer and every integer corresponds to a real number, and it's 1-to-1. There's no duplication, there's nothing missing. All right, so let's suppose you give me a function f which maps integers to real numbers. Okay, well, I'm going to start off and I'm going to write down a table of these. So I'm going to write down some number n, and I'm going to write down what f of n is. And I'm just going to start with positive n. And I don't know what these are. Let's just suppose this is, 1.24653 and a bunch of zeros. And maybe 2 maps to pi. And maybe 3 maps to, I don't know, just the number 1. And 4 maps to, good old 1/3, because that's always good for paradoxes. And 5 maps to, I don't know, 1.23456789012, and so on and so forth, right? And you claim to me that this function f maps every integer to every real number and every real number to every integer, okay? And I'll say, okay, I'm going to make a new real number. You tell me what integer maps to it. Okay, here's the number I'm going to make. The first digit, and let's just suppose we're dealing with numbers from 0 to 9 point something. So the first digit is going to be the first digit of this number plus 1. The second digit will be the second digit of the second number plus 1. The third digit will be the third digit of this third number plus 1. The fourth digit will be the fourth digit of the fourth number plus 1. The fifth digit will be the fifth digit of the fifth number plus 1, and so on. And I'm going to build a perfectly legal real number, and I'm going to say, okay, what integer maps to this? Because I don't see this number in this list. Well, you'll say, oh, it's not on that list. It's actually number 1000 maps to this. Well, guess what? The 1000th digit of f of 1000 maps to something different from the 1000th digit of this. the 1000th digit of F1000, whatever that is, I added 1 to that to get the 1000th digit of this number. Just like this can't be f of 5 because the 5th digit of f of 5 differs from the 5th digit of this. The 6th digit of f of 6 differs from the 6th digit of this. There is no integer that can possibly map to this number, because integer n will map to something that is not equal to this number. In particular, the nth digit of f of n will be different from the nth digit of this, by the way I constructed this. So you claim you have a function which maps bijectively from the integers to the real numbers. I just found a new real number that's not mapped to by any integer, which means this function cannot exist. And since it cannot exist, that proves that the cardinality of these sets is not the same. And in fact, R has a larger cardinality because Z is a subset of R. So that's a diagonalization argument. And it's so named because, we're moving along the diagonal here and doing something with what we find there. And it's a very powerful general construct. It's a way to lead to contradictions and, proof by counterexamples. All right, so that's the end of our time here. So Wednesday we'll start talking about logic and proofs and propositional calculus, and that will be the next major unit we're going through, and we'll do that for about a week and a half, and then shift gears into number theory, then come back to proofs and logic and dig deeper into it. All right, so I will see you next time. Thanks.